Okay, anyway, we can start. So today's topic of interest is timing attacks, whether or not they're still practical in regards to web applications. And we're saying web applications because timing attacks are usually a methodology studied in cryptography, in the field of cryptography, and that's not pretty common in web applications nowadays. The main reason for that, or reasons, we'll be speaking about later on, but for now, this is the topic, and the things that we'll be discussing. Yeah, this doesn't work, obviously. So the topics that we're going to discuss today is what is a timing attack, because there are different types of timing attacks, but in the field of cryptography, it's quite different. So in this particular case, we're going to go over a specific case of timing attacks. We'll go over what our plan was for the presentation, what we did differently to other researches, because there's been a lot of research in this field, but obviously most of them haven't been carried out on web applications at all. They have been solely focused on cryptography, and this is because the timing side channel is famous in that field, and it's not pretty common in web applications. There's too many jitter and a lot of network latency that is pretty difficult to filter out, so this is not something that is usually done on a daily basis. So we'll talk about what we did differently than our researches. What did we achieve? Because first of all, we had a different goal for the target, but we ended up with a totally different scenario. We'll be generalizing timing attacks, and we'll be talking about how practical they are, which is the true meaning of the presentation, because as it seems, as of 2018, there haven't been any exploits in the wild for timing attacks. And finally, we'll be talking about a bit of MISC stuff about who are subjects to an attack, what is an acceptable solution, because a lot of people tend to think that trading off memory for execution time is a good idea. While this may be true to some extent, it's not entirely true, so we'll be discussing that as well. So this is a basic string comparison in PHP. We've taken PHP as an example, but this pretty much applies to almost any language out there. So the first thing we have here is a pretty exaggerated example and pretty simplified, so you can just get the idea, is that we have a variable key that is the MD5 checksum of any string. Actually, it doesn't matter. As long as it's an MD5, it's 32 characters, and what we have next is an if check, an if clause. We're checking whether the get parameter called key is equal to the value of the variable key, which is essentially saying that if it's not different, if it's not equal, then it echoes out forbidden. Next case, it echoes out welcome. So this is pretty similar to any authentication, with the only exception that authentications tend to be a lot more complex than this. So the problem here is that we have a comparison, and the comparison is not a constant time algorithm, which means that depending on what we input, it takes different amount of time to process it. Essentially, this is giving out a lot of information that shouldn't be exposed otherwise. For example, imagine that you're inputting your password in any form out there, authentication form, and once you've mistaken it, imagine if the form says, well, you have an error, and that's on position 5. Your password is not wrong. It's not correct. So this is the source code for the isIdentical function, because PHP, as we know, is written in C. That's the source code of C, of PHP, that's in C. And we have a simple switch case, which match up if the input string is a string type. First thing that we do on line 2 is that we compare whether the variables are the same. This is different from comparing values, just about variables as types. And what is of particular interest is the else clause, which is the thing that we're going to exploit in this presentation. We also have a demo included at the end. The first thing that it does, it compares the length of the strings. If they are different, it doesn't matter. I mean, we won't continue further. Obviously, if the length is not the same, the strings are not the same. So next thing we do is that we compare the bytes, 1 byte at a time. This is done by passing 3 arguments to memcp, the memCompare function. And the first part asks for the first variable, the second variable, and their length. So this is what the source code of memory compare is, actually. It takes two unsigned chars, U1 and U2, and it iterates over the entire string, so it counts it 1 byte at a time. And it basically says that if you're comparing 1 byte at a time, you want to index that as an array. And what you have right now is you take each and every single character and you compare it with its corresponding from the following string, from the second string. If they don't match up, an error is returned, or it otherwise says return false. So this exposes a lot of information, but if we can time it properly, if we can extract information from that, it would be great. But unfortunately, over the network, it's pretty difficult to filter out jitter, and that's not something a lot of people are eager to accomplish nowadays. So this is a pretty trivial example. Those are nanoseconds, but it's a pretty exaggerated example. It has nothing to do actually with real data. It's just to exemplify what timing attacks are, and in particular timing attacks that we're going to discuss now. So as we said, we have one key. Consider that as a checksum, an MD5. That's hexadecimal, and it's 32 characters of length. And the first thing we do is that we input any string, literally. If we find, let's say, the first 4 matches of the string, we get different times. But when you attempt to uncover the 5th one, and it's wrong, yes, it does process it. It does take some time, but it doesn't attempt to process the 6th character, because the 5th one is wrong. So it doesn't matter whether the 6th, the 7th, or the 8th, etc. are correct. Even if one's wrong, the whole string is not equal to itself. And you can see from this example that the 80 nanoseconds, we compare 3 letters, 3 symbols, to 5 and 6. The E, the 4th one, is incorrect. It takes time to process it, but it doesn't attempt to process the 5th one. So this means less time, less execution time, which we can assume that the next character is not correct. The main idea of this is to just try all possible characters until we find one that takes the most time. The one that takes the most time means that is the correct character. And this is another example that would show what timing attacks are, in particular the ones we're going to discuss. As you can see, again, the times are different, but they're still in a particular range of each other. So there's no spikes here, because obviously we have wacko data inserted. That's just a trivial example. So the times are pretty much the same. I mean, the difference of 4 nanoseconds doesn't really feel like much. And we have 95 nanoseconds for the first string. We have guessed 4 characters, and 91 nanoseconds for the second case, again, with 4 characters. Then we have the third example, which is 115 nanoseconds, but in this case, we have a total of 5 characters that we have guessed, and it attempted to check the 6th one. Whether it's correct or not doesn't matter, it takes more time. And clearly, 91, 95, and 115 is pretty different from each other. So our main idea for timing attacks, as we said, it's been studied in a particular field of the cryptography field, and it's not something that is generally used in web applications. So we had to make sure that we time each and every segment properly. So the first thing we had to do is time the round trip time, RTT, which is basically how many hops it takes to reach the destination and how long it takes for each hop to be processed. We also had to time the web server, its response time, and the response time of the application. And we should also consider that those times are pretty equal to each other, and they are self-contained. I mean, the application time, the time it takes for the application to process the data we input, is pretty much contained in the server's response time, so we have to filter that out. We have to know what the server response time is, essentially. We need to know all of these measurements. We take measurement of all 3 categories in order to just execute a normal timing attack. Otherwise, if we work only with the server's response time, without the application, without round trip time, it's pretty much a failure, and we won't be getting any reliable data at all. So the thing that we should mention before we can continue is a couple of prerequisites, because you need to know what we've had access to, what we've done different, and what our test cases was. So first of all, we had access to the source code. It's a PHP system that is vulnerable to timing attacks. And it also has vulnerability that is a pass the hash is present. Again, not so common in web applications, but apparently in this case, the developers considered that performing hashing on the front end was better. So they hashed the password just to save some execution time on their back end, forcing the user to compute his own hash using JavaScript. And then they were comparing the hash at the back end. So whatever was generated on the front end was compared on the back end eventually. We also didn't have any hindrance with web application firewalls, intrusion detection systems, prevention systems. We had no CDNs, we had no Cloudflare, no caching, no reverse proxies, no Nginx. And this is vital because in most cases, when you have any kind of a reverse proxy, it will just fill up the data. You won't have any reliable source whatsoever. Imagine the reverse proxy just standing in front of your web server and it just routes packets. We're actually timing its response time, not the actual web server. So this was a problem, and in this case, we had no reverse proxies in front of us. Obviously, a web application firewall or an IDS neither, because timing attacks tend to require a large amount of requests, and if we were to send out, let's say, 1,000 requests per second, clearly most web application firewalls or IDSs will stop us, and we'll be able to continue. So the thing that we started off with was, first of all, study the application source code in details, just so we can find a particular module, particular functionality to exploit. Usually that evolves around security critical operations like authentication, cryptography, and we know that those operations tend to take time because they process a lot more data, and it's pretty different to any other really implementation of modules and mechanisms. And essentially, it's one that exposes data. I mean, if we have a vulnerability in the authentication system, that's not a good idea at all. So we had to pinpoint a particular function source code that handles this data to exploit it. We conduct the basic data collection so we can just know what we're working with, as in information about the timing differences. And we had to work on improving the noise filtration, because the noise filtration is, if not the most important part of the entire timing attack. If we have a lot of noise, no matter how much requests we send, it doesn't matter. It's just a failed attempt whatsoever. So we had to figure out noise, and we applied several techniques, most of which were derived from another conference in Black Hat that we kind of copied a bit. And eventually, we had to reduce the search space for a timing attack. Yes, unfortunately, we have to test each and every character, which is 16 characters in total for 32 positions. This amounts to millions of requests that have to be sent in a reasonable time, let's say within an hour or two. Otherwise, we get a large CPU spike from the remote server, or there could be some other noise that is induced by the network, and that generally isn't a good idea. So we had to think of a way to reduce the search space. As a matter of fact, in this particular case, we had an idea of what to do, but it isn't really applicable in most cases out there. So those are things that we've attempted. First of all, this is part of what we did differently than our researchers out there. What we attempted to do, and we thought initially was a good idea, was to profile the application using Xdebug or shprof. It's a PHP application again, but as it turned out, this didn't work out well because the application itself isn't really a reliable means of data, and we had to resort to other techniques, essentially timing it locally without the usage of debugger, where we have a lot less noise. We also had to measure the round trip time. We've attempted to do that via TCP timestamps, but they don't keep that much data, and their lowest granularity is 1 millisecond to 100 seconds, and we're working with microseconds, so milliseconds are no good for us, and TCP timestamps go as low as 1 millisecond. So this wasn't something that could help us, at least not at first sight. And we also didn't get to make observations from user space because it induced a lot of noise as well. Working from user space implies that you have to handle a lot of things. For example, system calls. When you send a request and when you receive it, goes through the kernel, the interface card, and all of those operations take a large amount of time. I mean, a large amount of time is in microseconds, something that we really don't need as a time difference, and we had to filter that out. So doing that from user space, for example, using curl, burp, or anything like that, didn't work out. We had to trace system calls with strace, for example, but that was pretty tricky because strace is not easy to handle, and we also had to automate the process in the end. But what we did differently and what actually worked is timing each individual PHP function by itself. We've copied from the source code, we've done some unit testing, and eventually we just attempted to time it using the microtime function in PHP. We collected the data from several samples. For example, in this particular case, the samples we took were 100,000. And we also averaged out web service performance per version. Because different versions of PHP, for example, or Apache, because we've done PHP as well as an interpreter, tend to have different execution times. For example, PHP 5.6 is totally different from PHP 7. PHP 7 has a huge boost in performance, and that can pretty much cripple our attack to a large extent. So we had to handle that as well, and timing different PHP functions was our main aspect of the attack, because once we have a reasonable idea how long it takes for a function to get executed, we could essentially just subtract that time from the total time, and we can have some reasonable data to work with. So those were the few things we did differently from others, because I say others as in the presentation that was presented at Black Hat in 2015. They've only attempted to calculate the round-trip time. They've calculated the noise delta, and they worked with a lot of statistical analysis, like L estimators. Another thing that they used was the common filter. We used the common filter as well. But it turned out, in our case, the common filter is the only thing we needed, in addition to the timing of different PHP functions. So regarding the round-trip time, what we actually done to calculate it is that we didn't do it from user space. We clarified that because user space is not reliable, especially for networking. But what was pretty reliable was packet capturing. We captured a couple of packets. We estimated the time based on the synchronized and acknowledgement requests. And yeah, as I said, TCP timestamps don't work that well. Was granularity is 1 millisecond. strace can be tricky, and different protocols can be routed differently. For example, if you were attempting to guess the round-trip time using ping, ISMP traffic, you wouldn't be getting as much reliable data as using TCP stack. So we had to work with packet sniffing, and that was pretty much something that we had to automate as well. So packet capturing and then extracting information from it. And that's about round-trip time. Here you can see basic statistics of how round-trip time differs. This is a basic ping request. Those are the 4 criteria: the median deviation, the maximum value, the average value, and the minimum value. As you can see, it's quite a lot of noise here. We can't really figure out what reliable data is hidden within it. And if we just leave out an average value, it doesn't work out as well, because one little spike can rear off the charts. And using TCP ping, which is another utility, but instead of using ICMP requests, it uses TCP once, was also not a great idea, because as you can see, it's pretty different from a smooth graph that would otherwise represent reliable data. So we couldn't use any of those. We had to resort to something else, and packet capturing was that. We had to capture packets using Wireshark, let's say, or TCP dump, and we calculated time depending on the differences. And this is how the SYN and ACK packets look like. When we apply the common filter, the graph is a lot smoother, and this is pretty much data we could work with, in addition to the timing of PHP functions and averaging out web service response time. Because, yeah, I mean, Apache 2.2 is taking a bit more time than Apache 2.4 of the scale of nanoseconds, microseconds, but this does matter to us because we're aiming to time this as perfect as possible. we can't afford to lose any microsecond at all. And as you can guess, this induces a lot of noise, which is otherwise not preferable. So this is what a basic packet capturing looks like. We've filtered out most of the data so we can represent it in a sensible way. The XXX IP is ours. This is the host's, the target, YOY. And the first thing we do is send an HTTP request with the size, the protocol version, request method. And this is the current timestamp that is on our welcome computer. This is the first response, the acknowledgement packet. And in the end, we have essentially the status code. There's actual response from the web server. So as you can see, there's quite a lot of difference here, as in time differences. And if we were to measure from the time it took from the first request, hours, the response time of the server, that's totally different. The response time is actually the acknowledgement packet. And we had to use this data to work with and get some reliable statistics so we can later on work with our timing attack in order to filter out noise. That's essentially the biggest part of the entire attack. Filter out noise so we can have reliable data and then basically flood the server with a lot of requests so we can just get a lot of metrics and figure out which character is the next one. So spikes were another case which kind of bug out our statistics. You can't always predict, you can almost never predict whether a spike can occur and how it can differ from time to time. So imagine that a process with a higher priority than PHP's process is running. It can simply affect it up to the scale of nanoseconds or microseconds, and this would pretty much bug our data, and we won't be able to get anything out of it whatsoever. So what we did to reduce that and actually calculate how long it took on average was by mirroring the target environment. We've essentially done some reconnaissance on the target side, and we figured out it's using a certain version of Apache up to the minor version, 2.429, I think. So we timed how much on average it takes for Apache 2.4.29 takes to execute certain requests. We did the same with PHP and pretty much anything that we knew we had information about. So we could just subtract that from total time, and that's just averaging out stuff. So the application profiling, the function timing is the most important thing we've done, and the thing that pretty much made our attack successful in this particular case. But this is not usually the case in most web applications, because what they do is they hash a value, they store it, and when you input a string, it hashes it and compares it. So this is totally different. We're not working with string comparison there, and I'd say they're not skeptical timing attacks. But in our case, we had a pass the hash vulnerability, which essentially allowed us to provide a hash instead of a password. And this pretty much means that we can authenticate without having the plain text of the password. We can just provide a hash. A couple of developers consider that a good practice, but in general, that's a pretty bad idea because, yeah, it's true that you're transmitting the password encrypted, in this case hashed, over the network. In case somebody sniffs it, he'll be intercepting the hash, but at the same time, he'll be walking with the hash. He wouldn't need to crack it because our authentication mechanism is using the hash value instead of its plain text value. So, yeah, we've calculated the execution time for different environments, and we also calculate the median absolute deviation. This is just something that we could refer to as time differences or variance. And it turned out to be a pretty useful statistic in our attack because it helped us improve the analysis by, I think it was 15, 30%, which was pretty huge at this scale. So the target, more specifically, what we had is we've extracted some of the functions here so we can visualize it easier. We have the isValidHash function, which just checks whether the hash is valid or not, so we can know whether we should even process it. And what this basically does is it just compares the length. If the length is not equal to 40, basically not a SH1, a SHA-1 hash. And if it's not hexadecimal, it's not a hash either. So if neither of those, if both of these are not confirmed, it returns false, otherwise it returns true. So once we use that down here in the verify password function, we can then proceed with the string comparison. We compare the user password hash with the one that is stored on our end, database in this case. And this is, again, using a non-constant time algorithm. As we look the is identical function in the earlier slides, it's comparing one byte at a time, which is not a good idea. It induces some vulnerability that is essentially a timing channel. So this was not a good idea at all from developers, but they haven't figured that past the hash vulnerabilities are that much of a concern, and they were more like relying on performance rather than security, like saying you can't obtain a hash, so basically you can't log in, so it doesn't matter if I've implemented the past hash vulnerability or not. But anyway, in this case, all we had was we needed to time how long it takes for a hash to process, one character at a time, so we can essentially guess the next character, and etc. So this is how the execution time of the isValidHash function works like. It is up the scale of microseconds this time, 5,000 microseconds in this particular case. And yeah, there is not a lot of noise, but still, we would like to smooth that and have more reliable data to work with. Because what we've done is time this particular function, how long it takes under different PHP versions, and in particular, the client was using, let's say, PHP 5.6. So we had the execution time subtracted, but at the same time, we were calculating during the runtime as well. And this is the verify password function, how it resembled a similar graph, but different time. This time is 19,000 microseconds. A lot different and takes a lot more time to do that comparison. That's because it does the string comparison here, in addition to the verification of the hash. So this is something that we're focusing right now. This is the vulnerability in the system that we're trying to expose and trying to bypass the mechanism by trying one character at a time. But unfortunately, in this case, some rough statistics means that on average we have to send 14,000 requests, and this is pretty much, I'd say, not a huge number for now. Usually it takes a lot more, like 50,000 or 100,000. But this was like 2 hops away from us. We had reliable statistics, and we also worked with the server itself. We had access to the server as well, so we had the possibility to time its particular response time locally in this case. So the example is pretty much exaggerated, just to demonstrate the attack. But the main idea is the hash is 40 characters. We have to guess it one character at a time. It's hexadecimal, and we know that hexadecimal contains 16 elements. It is based on A to F, 0 to 9, 16 characters that we have to try. And this essentially means that for every element, we have to send out 14,000 requests, and that's per every position as well, which means that on average, we have to send out 224,000 requests per each position to guess a single character, and that's on average. This could range up to billions of requests, millions of requests. Nobody would naturally allow us to do that. And in total, for a full hash recovery, in this case is the secure hashing algorithm 1, SHA-1. It would take about merely 9 million requests for a full hash recovery. And as I said, this is again greatly exaggerated because otherwise we would have billions of requests sending out. And we are also expecting a response from the server. So this is another thing to look up to. We have considered like a window of 2 hours, and in those 2 hours we have to send out 9 million requests. Usually we won't be allowed to do that. So a lot of people were wondering when we did our research online, we read a lot of topics on forums, a lot of opinions expressed by other researchers. They were wondering what is the difference to brute forcing? Is there any actual usage of timing attacks? Well, there is, and yeah, it is really quite simple because it works for any password, no matter the complexity. In this case, we're not cracking the hash, we're recovering the hash, not the plain text behind it. So in this case, let's say that our password is totally random, 20 characters of length, using a wide variety of characters. Say our character set is 64 of length. That would take a large amount of time if we were to attempt and brute force it, because essentially this roundabouts to, I know, trillions of requests, trillions of combinations, and we have to try each and every one. So brute forcing is preferable in some cases. This is if the password is predictable. Considering the password is whatever, or test 123. Yeah, brute forcing would be better because it would simply contain this in a couple of iterations, or it would be in a word list, one of the top passwords, so to say. Otherwise, we would be trying a timing attack against something that is fairly simple to guess. So yeah, I mean, the basic idea is if someone attempts to target a system like that, he should first perform any word list attack, mask attack, brute force, and only then, if nothing is recovered, resort to timing attacks. Timing attacks are not practical at all in web applications, and the only difference is that it works on any user's applied input. In this particular case, the pass the hash vulnerability. So reducing the search space essentially means that we have to reduce the number of attempts we're making, because 9 million requests are a lot. And as I said, it's exaggerated, so they're billions actually. And this is not a good idea to usually go about. We had to do something about this, and in this case, as we said before, this is a pretty weak authentication mechanism. It was like intentionally vulnerable, so to say, because not a lot of developers are using such mechanisms for authentication. For example, in this case, we had a simple message digits function. I think it was MD5, but we later on tested with SH1, it worked as well. And the length is 32 characters. We know that. We know how an MD5 is built. We know what it consists of. And if we were to attempt each and every possible element, it would take a total of 9 million requests. Not a good idea. So what we do differently is that it wasn't necessary to recover the full hash. You know, search space is incredibly big, and we wouldn't need to recover the full hash, because if we have, let's say, the first 4, 5, 6, or 10 characters, doesn't matter, we could just look them up in a rainbow table of pre-computed hashes and store plaintexts corresponding to them, and say like 50 or 40 pop out to be certain matches. We could just try those passwords manually or automated, doesn't matter. But the main idea is that we can just identify a hash by the first several symbols. So that kind of reduced the search space a bit, but considering that the hash is in a rainbow table, and rainbow tables tend to be quite huge in terms of storage, we needed like 2 terabytes of data for just basic rainbow tables. It was basically alphanumeric of the length of 9. And that's assuming the user uses a password, one of those. But the main idea here is that we've taken this from an online attack to an offline attack. Once we have the hash, we can work with it. It doesn't mean that we should brute force and expect an answer from the server. Once we retrieve the hash, we can just do an offline attack where we have no limitations. And this is a bit of a statistics. Well, the first 10 characters are expected to be recovered with 2 million requests. Based off of this, the elements we pick multiplied by the number of requests per element, multiplied by the length, because we need to apply this for each and every position, up to the full length. So if we were to say recover the first 5 or 6 characters, this would take a reasonably low amount of requests in comparison to a full hash recovery. And 13 characters take up to 3 million, and that's 4.5 million. So it's still better, a lot better than 9 million requests, and we can work with this methodology for other vulnerabilities, not only the pass the hash. So we can switch to demo now. So we produced a pretty simple and simplified tool for this particular case. And I exaggerate, and I focus on this particular case because we've written this tool for one specific case. And that case is the pass the hash vulnerability that is present and that we've exploited. What this tool actually does is you feed it in some data. The data is essentially the URL to target the page request, where it goes. You also have to specify the data that it accepts, otherwise it won't know what to send, what to expect. And it does some statistics. It estimates the transfer rate so we can know the throughput and how many requests we can process. It also checks for caching, because as I said, caching would be a huge problem if we have any sort of hashing. It would not be a good idea at all, because caching would just cache our requests. We won't be able to get a reliable data. We won't be communicating with the server. We'll just be receiving a cached copy. And in this case, it detected mod deflate, but mod deflate is not a problem. It's caching statical resources, and it's not something that can bother us. What we're looking for is dynamic requests, and dynamic requests only. And next is checking for, that's the timing. Let me just check. Yeah, it's pre-recorded. First thing is the caching. It checks for any rate limiting, which is essentially a web application firewall, an IDS, an IPS. And after it filters that out, after it finds whether there's an application firewall in front, it continues on. Obviously, if there is one, it wouldn't continue, because it would be a huge problem with the data we're working with. It also does automated calculation of the round trip time, using the difference between the synchronized and acknowledgement packets. And once it calculates that as well, only then can we have the timing attack executed, because we need to have some data to filter out. We need to subtract that data so we can get a rough estimate of what is going on. It might take a couple of seconds. It's a pre-recorded video, because a real-time attack would take a lot more resources, and we wouldn't be able to execute it here on stage, especially over the Wi-Fi. And considering that we've done this over 3 hops away, here it might have been, depending on the routers, but it could have been 7, doesn't matter. So okay, calculate the round trip time. It said the data is reliable, it's stable. So round trip time, it does several measurements of round trip time using different methods, not only the synchronous and acknowledgement packet differences. It does also ICMP traffic, as we mentioned earlier, and a lot of other information that is retrieved from different sources. So it calculated round trip time. It said how many hops away we are and what is the web server's response time. It saves all of this information in its memory, so it knows what to subtract, when to subtract it. And what we are doing now is just, it prompts you to, whether you want to use statistics from this particular version of Apache 2.429, because we had local statistics loaded prior to this attack. That is the average time it takes for this particular version of Apache to process requests. And yeah, we've decided to use the statistics to reduce the noise. Does some basic request statistics, how many requests on average it would take for us to execute the attack. In this case, it's 47,000 requests, which is, per element. It's not a low number. It's a pretty huge number, and we have to multiply that by the character set length, which is 60 in this case, and then multiply all of this by 32. If we were to check an MD5, for example. If we were to check on SHA1, it would be 40. And imagine if there was a SOUT. It would pretty much render the attack useless. So in this particular case, it already started. So there's a couple of statistics before that as well. It said that on average the attack might take about 37 minutes, depending on transfer rate, but this is not much accurate. I mean, it's just roundabout time it would take, because we can't really calculate how long it would take. And what it does now is sends samples of data, 47,000 requests, and this is done usually in a time frame of, say, a minute or so. So it checks each and every single character to see how long it takes. It does some statistics based on that. And we're essentially checking each and every character. We're calculating the median absolute deviation here. We're also using that to subtract it, to know how far from the local difference that is, the deviation, and we have variance. This is something that we've induced in the tool. how variable is this result from the different ones, from the previous ones. So the first few ones are not really reliable as an information source. Obviously, if we retrieve more information, it will be pretty clear that the variance is tolerable. And this is the confidence level, something that we have invented again, something that says how confident is the tool about this data. We've also worked for identifying spikes within the tool, but that was a bit tricky, so we couldn't implement it eventually. And right now it's checking up to the length of 5, because we might have a full hash recovery, but we've talked about that. It takes a lot more time to process and a lot more requests. So in this case, we were prompted and we chose to use 5 positions, to time 5 positions, and then look up those first 5 characters in any rainbow table, so we can just find hashes that start with this particular pattern. And we could basically make an assumption that maybe one of those hashes that are contained in rainbow table that matched are our user's hash, essentially the password eventually. So this goes a long time. It's actually 47 minutes. We won't be watching the whole of it because data is pretty much the same. You'll be seeing the same over and over again. Eventually, it ends up calculating the first 5 characters, and as I said, we can look them up in a rainbow table, and essentially find the hash. So in this case, we can just skip the video and see if I can do it from here. Or our colleagues from DefCamp can just switch the video back to presentation. Can we go back to presentation, please? So first thing we're going to talk about after the demo is what the consequences can be, because a lot of people overlook this type of attacks, but it's not that unusual to see them in the wild, especially if the attack is targeted against a specific system. And we've also done that. We've attempted that to WordPress, but WordPress doesn't use the same methodology. It doesn't do pass the hash. You inputted a password, and it hashes it on the back end. But this doesn't apply only to pass the hash vulnerabilities. It also applies to a wide range of vulnerabilities that could induce a timing channel, because most developers are concerned about the performance more than the security aspect, and essentially they don't even consider timing attacks practical at all. To a certain extent, they're not practical, but in specific cases, they could turn out to be quite more practical than a simple brute force attack. And the consequences can range from a complete takeover of the server. This is something that could be the final goal. It could be achieved, although in rare cases. And considering that the attack has been running for a long time, this also induces a lot of resource exhaustion on the server. If costly operations are performed, an example, the authentication system might do some crypto on the back end, in addition to the comparison, and this takes some CPU time. Essentially, if we're sending out thousands of requests, it would just sum up and it would exhaust a lot of resources, if you're even allowed to do that. Cloud Linux protects against this, for example, and Cloud Linux is available in almost every cPanel out there, almost any shared hosting environment. And it's basically something that says you're limited to those resources, you can't use any more CPU time than this. So this would pretty much, wouldn't be a problem in this case, but in general, it could turn out to be a problem over an extended period of time if there is no limitation at all regarding the number of requests we send. This could turn out to be a problem. And the basic solution to timing attacks, we've read a lot of papers online. Something that a lot of people express an opinion is that you should just compare each character. Doesn't matter if it's right or wrong, you compare the next one as well. So it's a constant time function. And this pretty much applies mostly to security critical operations. One such example is the authentication again, as I say, because this is something that handles our data. This is something that handles the authentication of a user, which is essentially almost everything in today's systems. And of course, if you have a rate limiting policy, if you have caching, if you have a reverse proxy, pretty much renders our attack useless. So even the smallest things can hinder the attack. Consider that the user is using opcache in PHP. That would might as well just ruin the attack totally. And we will be working with quite useless data from then on, which is not a good idea at all, but yeah, we will be wasting just time with that. So enforcing a rate limiting policy saying that this IP address is about a couple of requests per second and requests per second would be a good idea. And the usage of constant time algorithms is really the key aspect. If we rely on just third factors like caching and rate limiting, yeah, this would most probably limit the attacks, but they will still be possible, no matter how small. And yeah, a lot of developers who are also relying on network jitter. We followed up a couple of GitHub repositories when there were issues have been submitted from the community. They were saying that, you know, there's a timing attack here, and the developer was simply replying that there's a lot of noise, so they won't be able to exploit it. Eventually, this was in case of the system PIWIC, the statistics system. It was actually exploited in the wild, and it turned out that this is not something that you should generally rely on. Network jitter, yes, it does stop you, but as we saw earlier on, we can figure that out as well. And coupled with a rate limiting policy, a caching server, something that we would naturally have anyway, this would pretty much render the attacks totally useless. We won't be able to utilize them in any way possible. And last but not least, I'd like to give some kudos to these two researchers. The second one of Patrick Brady is it's pretty technical, and it's something that pretty sparked the idea of timing attacks back in 2010 when it was possible to time it up to nanoseconds. We couldn't time it up to nanoseconds. We managed only to microseconds, but it would be a lot more accurate if we could, you know, go down to nanoseconds. Unfortunately, that is, we didn't find it possible in our case. And the first one, the opportunities and limits of remote timing attacks, is something that also had a lot of news about it. A lot of people were talking about this. Of course, the Meltdown and Spectre exploits were essentially using a side channel. It's a bit different from this. I should rather say totally different from this one. But again, it was a timing attack, and we all know what the consequences of Meltdown and Spectre were. They weren't patched immediately, and yeah, this was a pretty different story. So that's about it. If anyone has any questions, I'm guessing there will be a lot of questions asked. Now is the time to do that.
Thank you very much for the presentation. We'll be taking questions in turn. I think that was the first hand raised in the first row. My colleague will be coming with a mic.
Thank you. Just a quick question. Some people suggest to use delays, random delays. What's your opinion on that?
No, random delays are not a good idea because you can still average out the noise. You can still average out how long it takes. For example, you can send out, let's say, 12 requests, 20 requests, 100 requests. Depends on the data and how much noise induced. And you can still average that out. You can just, you can also predict the output if the entropy is too low. But that depends on the source. If you're using defu random, for example, in Linux, that won't be possible. It will still hinder the attack to a great deal, but it would still be possible. The vulnerability will still be there.
Thank you.
A second question.
Hi. How can you find the best timing?
What do you mean by the best timing?
So you will set the request and a delay for a few seconds or maybe
Yes.
a few minutes, but do you have a method to find
The one that took the longest?
Yes.
Yeah, that's essentially the character that is considered to be valid. In other words, but what we've done is that we've sent 47,000 requests for each and every position, each and every character for each position. And on average, depending on how long it took for each and every single, we managed to just establish a basic statistical analysis. When you could say that this one took, say, 100 microseconds more than the previous ones, was basically the one that has the most execution time. But we do that by sending a ton of requests. In this case, 47,000 per position.
and this maybe make you vulnerable to.
What do you mean?
Create some noise when you do that.
When we send out 70,000 requests or 47,000?
Yes. No.
Well, that would depend. As I said, the statistics is greatly affected by almost any factor out there, so we can't really work with reliable data all the time. As a matter of fact, this particular recording of the test script was done after the 4th or 6th attempt, I don't know, until we could get this working, essentially. So, yeah, it is possible. Quite possible, yes.
Thank you.
We have our next question in the third row there, and then going to you, and then here, okay?
Okay, so most of the CMS actually using to reset the password using a link with hash.
Yes.
And there is no limit on how many requests you can do on the reset password link.
Yeah.
So isn't the best way not to attack the password but the reset password hash?
Yeah, but in this case, we wouldn't know which hash we're resetting. In order to do that, we need to have, it depends on the system, but what they usually do is they, whenever password request is being sent, they generate a hash for this specific user, and then you have to guess the hash for this user. But consider that a system is more scale, the website is widely used. Consider that a couple of users have requested a forgotten password at the same time, or the similar time frame. We would recover a different hash, possibly. We wouldn't know which hash would be for this particular user. So it's kind of a logical issue here because we wouldn't know how to match up this hash to this specific user. We might as well reset the password to another user in this case.
Next question was somewhere here. Yes.
Hello. As far as I know, in these days, web applications sold password hashes before storing them in databases.
Yeah.
So isn't that actually the best solution about around the timing attacks?
Well, it wouldn't make this possible, certainly. But in this example, the developers had no understanding of security at all. And the idea was to just present a simplified version of the attack. But if you're using bcrypt, for example, if you're using Argon 2, doesn't matter. As long as it has a hash, as long as it has a pepper or salt, that would pretty much render attack useless whatsoever, yeah.
Okay.
And this is also if you have a passive hash vulnerability, which is not something you have in almost any application out there. So it's not really practical at all, the timing attack. Yes, a salt would totally render it useless. Unless the salt is static. I mean, if you have one single static salt for each and every hash.
Thank you.
Thank you. Our next question here. And is there anyone else, or will this be our last question?
Hi. Actually, I have two questions, if you may. How often do you use timing attacks in your pen test engagements? And secondly, what's the best result that you could get?
Well, we don't naturally use timing attacks in our penetration tests because we kind of focused on more reliable vulnerabilities. Timing attacks are something that is something of last resort, so to say. If we haven't found any other vulnerability or if there's something specific to the application that could be exploited and we have in mind that it could be exploited, we will attempt that, but it just requires a lot of research, a lot of resources. We've spent about, let's say, a month and a half on this specific case, and this is not practical at all as well. So they're pretty much not practical, and this isn't something that we do on a natural basis as penetration testers. Obviously, if a client asks for white box testing, and if he asks us to test for timing attacks in particular, we will do that, yeah. But not in general case, no. Not in general case. The best result on timing attacks is just to make string comparison constant time in critical operations. I'm not saying make the entire code, constant time, because that would be totally nonsense, but the idea is for security critical operations like authentication and cryptography, make it a constant time algorithm so it takes the same amount of time for each and every input. That would be the best thing to do. Of course, you could also bypass that, but this is something totally from the theoretical field. Depending on how much CPU it takes, you could still time it, but that's totally off the charts. I don't think that is even possible nowadays.
Cool, thank you.
Thank you. If we have any other questions, otherwise we will be finishing here. Thank you so much, Ivan. And let's
Thank you.